Hello, and welcome to this short taster lesson for A-Level Physics. My name is Dr. Parslow, and during this short session I'd like to give you an insight into one of the topics that we cover when we first start the course in September. Hopefully this will give you an idea of what a lesson may look like and the sort of topics that we'll cover during your first year. One of the first topics that we cover when we start A-Level Physics in Year 12 is quantum physics. This is a picture from a film called Angels and Demons, which you may have seen. It's a relatively recent one, but also you may have read the book by Dan Brown. In the film, they had some antimatter, which was contained in the picture at the bottom left, which was released, which then reacted with matter around us, causing a huge explosion and a release of energy. One of the topics that we look at in the quantum physics course builds on what you've looked at in year 10 and 11 and before that in Key Stage 3 about the subatomic particles, the neutrons, the protons and the electrons. We look at the other subatomic particles that make up these particles in the first place, and also what we call antimatter, that thing that caused the explosion. What's the difference between matter and antimatter? Why is there no antimatter around us? Otherwise we'd see those explosions all the time. Who predicted the existence of the antimatter, and how can we find it and detect it? This is Paul Dirac. He was a British physicist from the turn of the century, a contemporary of Einstein and all those other scientists and physicists that were discovering quantum physics at the time. As well as being a physicist, Dirac was a gifted mathematician, and he solved something called Schrodinger's equations, which then gave him two solutions, like a quadratic does in the maths that you have seen at GCSE and will do at A-level. And the positive solution to that gave us the electron, or the matter that we have around us. But then he also found there was a negative solution, which was then predicted to be antimatter. Now it took a long time to find that antimatter. Antimatter was not easy to find, because as soon as it comes into contact with matter, it combines and just releases energy. Another physicist called Anderson first found the evidence of a positron being the antiparticle of an electron. He found vapor trails caused by these particles moving through a very cold gas, and that caused condensation, much like you find from high altitude jet planes moving through the atmosphere. The interesting thing about these vapor trails is that they go in different directions, and the directions and the size of these trails gives us evidence for the existence of many different subatomic particles. As you know from your GCSE studies, when a charged particle interacts with an electrical or a magnetic field, it does different things. The direction of motion will be caused by a different charge on that particle. So a positive charge will go in one direction, a negative charge will go in the opposite direction. From the picture you can see they go different ways, so that shows us we have a positive and a negative charge particle. How far they go and that radius of curvature depends on the mass of that particle. So a particle with a larger mass will have a much more larger radius curve on it, whereas a smaller mass particle will have a much tighter curve. Now, an antiparticle is defined as the opposite, if you like, of a normal particle, the ones that we have around us all the time. It has exactly the same mass, but it has the opposite charge. And all the particles that we know of also have their corresponding antiparticle. They are very difficult to detect, as you can imagine. We generally only find them in terms of high-energy collision experiments in such places as the Large Hadron Collider in CERN, interaction with cosmic rays in our upper atmosphere, and also radioactive decay. As well as electrons being given out by unstable nuclei, they also give out positrons, the antiparticle of the electron. All of these antiparticles have an incredibly short lifetime, and it's incredibly difficult to isolate them for any amount of time to do any experiments with them. Now, I mentioned before, when we saw that other picture of the particle and antiparticle being produced, that different tracks showed the different properties of those particles. As you can see on this picture, the red trails are positrons. We know this because of the way the direction of the magnetic field is compared to the direction of the plane of the screen you're watching. So positive charged particles are moving up the screen and negatively charged particles down the screen. The different radiuses could be caused by different masses, but in this case we've got ones, different particles with different amount of energy. So the faster moving particles have a very large radius, whereas the slower moving particles are then curving back in with a smaller radius. As they lose energy, they curve in tighter and tighter and tighter till eventually those positrons will combine with the electrons around them, releasing energy. Now, one of the ways I mentioned that we could generate antimatter was with the interaction with the upper atmosphere. A gamma ray, or a photon, interacts with the high energy particles in our upper atmosphere. It interacts with the electric field that is generated by those particles, and this can cause that gamma photon to instantaneously change into matter, essentially mass. Mass is just a form of energy. This will cause a positron and an electron, or basically a particle and an antiparticle, to be formed. This is called pair production. The opposite also happens, and this probably introduces the best word that we have at A-level physics: annihilation. So this is representing what we saw on that first slide at the beginning of the lesson, with that explosion, where the antimatter and matter particles came together, reverted to the form of pure energy, and released all that energy in one burst. Now, quantum physics is that word that we've used a lot so far in this lesson, as one you'll also hear of before, and quantum means packet or parcel or small amount of. These photons that have the energy when they interact with our atmosphere, or when in the Large Hadron Collider experiments are done with them, have to have the correct amount of this energy to then go on to produce these pairs of particles. You'll have seen this idea of quantization before at GCSE Physics and Chemistry, when we talk about energy levels in terms of how the electrons drop down energy levels, not necessarily in shells, but then they release that energy in terms of luminescence. We see those in terms of the lights above our heads in fluorescent tubes. Those electrons are excited, they re-release the photons, and they give out these energy levels. Now, one application of antimatter is actually medical. You may have heard of MRI scanners, CT scanners, but there's another one called a PET scanner, which is called a positron emission tomography. This uses the positron, which is emitted by a radioisotope injected into the patient before the scan takes place. These positrons pass through the tissue, and then they will interact with electrons, causing annihilation and energy to be released in the form of photons. The annihilation produces two photons of equal energy. One travels in one direction and the other 180 degrees away from it. They are then detected by the scanner outside of the patient, and this information is then used to build a picture of the tissue inside. So hopefully that's given you a flavour of a typical topic that we may be covering in Year 12 Physics. It's taken us through the ideas of what antimatter is, the difference between matter and antimatter, and I'm sure now you understand why it's notoriously difficult to detect around us. We went through the history of why this was a mathematical concept that then turned eventually into an experiment where it detected the existence of antimatter. And also we've gone through the ideas how we can detect it and see evidence of it around us today, and a use in terms of medical applications. I hope you've enjoyed this lesson, and I look forward to seeing you in September when you start your A-level studies.